Sharing my screen. Um, Hang on. I was having issues with this earlier. Can you see it? Yeah, good. Okay. And I couldn't get it to go into full screen mode. It wouldn't share it over it, but okay. So I guess it'll go that way. All right, so thanks for the opportunity to speak and tell you about this. I'm going to start with some old history before we get to the current problems, just because the thing I'm going to focus on is how we go from a combinatorial problem to a dynamical one and back. So the parts I'm going to start off with is how to do this in a simpler setting than we need it for in the context that I'd like to discuss. And the simpler setting is that you take a finite coloring of the integers. While there are a lot of theorems that say we know a lot of monochromatic different patterns, and one of them, the oldest one, is perhaps Schur's theorem, which says that there's a monochromatic triple, meaning that satisfies that sum of the first two is the third. So A plus B is equal to C are all the same color. Okay, so the setting is you took the whole integers and you chopped them into finitely many pieces. That's what I'm calling a coloring. I'll call it either partition or coloring, either way. And one of them, in one of the pieces, you find this pattern. And there's lots of others. There are famous ones like van der Waerden's theorem, which says that there's a monochromatic arithmetic progression of whatever length you're looking for. And there's another one, which is Heinemann's theorem, which says there is a monochromatic IP set. And what that means is there is an infinite sequence, that looks like A1 less than A2, and so on, such that that whole sequence is the same color, and all the finite sums from this sequence, they look like A1 plus A2, A2 plus A3, A1 plus A3, A1 plus A2 plus A3, and so on. These are all the same colors. So that's what's an IP sequence. So that's very different than the first two. It's an infinite one, and we'll come back to that because that's the type of patterns we're going to focus on later. So let me give you a general definition, and please, stop me if you have questions. Don't wait till the end to interrupt. A collection of subsets of the integers, it has said to have the partition regularity property if whenever you look at a finite partition or finite coloring, then there is one P in the collection that is all in one element of the partition. Okay, so for example, P being arithmetic progressions, that's exactly van der Waerden's theorem. And we're going to translate that definition, let me leave it on for a moment, that definition of partition regularity that I have here, I want to translate this to dynamics. And the context in which this gets translated is into a compact metric space with a homeomorphism acting on it. Okay, so when I say a topological dynamical system, what I will mean is that X is compact metric, T is a homeomorphism. And now I want to show you how you translate partition regularity into something dynamical. Okay, so fix an epsilon. Since the space is compact, you can chop it up into finitely many pieces. These are the Y right here, the Y1 union YR. The number of pieces here is going to be exactly the corresponding to the partition that we started with over in the integers. But for now, all I care is you've chopped it up into any which way, Y1 up to YR, where the diameter of each of these pieces is less than epsilon. Okay, so the epsilon that was fixed here. Now, if you take some X in my space, I'm going to tell you how to get a partition over in the integers, in a coloring or a partition. And what that is I will say that I stick N into the jth color, or N is in CJ, if and only if when I iterate that point that I fixed right here, X and X, if I iterate it N times, it lands in the jth piece of my partition. So you're taking some point and following its orbit around the space and saying, here is my space chopped up into the pieces, Y1 up to YR. And now I take some point and I just follow it along and see where it goes. And you color it by which piece it landed in. So if I knew that the collection P were partition regular by some reason, let's say I knew van der Waals theorem, for example, and this were arithmetic progressions, then that would tell me that there's some P, you can think of it as progressions if you like, such that P lives entirely in one of the pieces. But dynamically, what that means, because we've defined this X to follow orbits, it means that all of these iterates for all these ends in that piece, okay, just following exactly from the definition here of how the X is defined, this dynamically means that all of these pieces are in a single Yj, in the same piece of the partition. But we also pick those Yj's to be very small in diameter, which means that they all lie in one little epsilon ball. So we've accumulated all of these iterates where maybe we're iterating along some collection P or arithmetic progression or something else. Okay. So what I've just done is I have actually defined and taken that original definition of the partition regularity and defined a new notion from it, which is dynamical regularity. And what we showed is that if you are partition regular, you are dynamical regular. So let me give you the definition. Okay, so the definition, a collection P is dynamically regular if for any space, and remember this is a compact metric space with a homeomorphism, any point you pick in it, any epsilon that you pick, there's some thing from that collection, maybe it's an arithmetic progression, such that all of the iterates along those for all those n in that particular P lie in the same epsilon ball. Okay. Is the definition clear?
Sorry, I just had one quick question. This might just be a silly extra thing. Are we typically assuming that T is like topologically transitive, or depending on the point, can we like miss some of these partitions?
There is no assumption right now on T being transitive or minimal or anything else. Later on, we will need stronger assumptions, but for the moment, right now, this was for only assumption here was that it's homeomorphism.
Okay, thank you.
Yeah, and definitely just ask questions. Don't let me keep going if I'm not. Okay, but the little argument that I gave you was that partition regularity implies dynamical regularity. Now, if you knew lots of partition regular results, then you would get some dynamical results out of this, but the real interest is the converse, to prove something dynamically and then go back and use it to prove a partition regularity result. So what I'm saying there is that the partition regularity is if and only if a collection P is partition regular, if and only if it has the dynamical regularity property. And so let's prove that converse direction, because this will be useful, is if you take a finite partition, I need to show you that when you have some collection, if it has the dynamical regularity, we're proving now the converse, that it has the partition regularity. And so what I'm going to do is start with that partition that you're given and define the right system to choose. And so this relates to the question that was asked, is now I want to choose a particular system to work with, not just an arbitrary one. But if I knew the dynamical regularity, then I apply it to that particular system. So how do I define the system? Well, it's going to be a left shift. Okay, so the system will be the shift on our symbols. Those are the colors that we used or the pieces of the partition. And I'm only doing it one-sided. We could make it two-sided, but I'm just, for simplicity, let's just argue it with one-sided now. And T is the left shift, so it moves every entry over by one. And you can pick any metric that's going to tell me that 2 points that agree at the beginning are going to be close. And by close, I just care that the distance is less than 1. So I want, let's say, the first entry of X and the first entry of Y sequences to be the same, a metric that does that. And there are lots of choices of metric that you can pick for this. And now I'm going to tell you what the particular point is. It's going to be an infinite sequence in the colors 1 through R, or in the alphabet 1 through R, where you define the ith entry of my sequence to the nth entry of my sequence to be I, if and only if n is colored with color I. Okay, so this just is reflecting what the coloring was doing in the integers, but it's a point in my dynamical system. And now if I know that it's dynamically regular, the collection P that I started with is dynamically regular, then there's some P, some instance, like maybe it's arithmetic progressions, such that the T to the NX's all lie in some epsilon ball. That was the definition of being dynamically regular. But what does it mean if they all lie in one epsilon ball? If you look at the definition of the metric, well, this actually tells you something. It tells you that because of the metric, it means that the T to the NX's, their 0th or their first entry, actually, this first entry at least, are all going to be the same, which means that the XNs are all the same for all N in that P. They must have been assigned the same color. Okay. But that tells me that the whole P was assigned in the same piece of the partition, the same color. So this proves the converse, that dynamical regularity implies partition regularity. So this is the simplest instance, I would call it a baby instance of the Furstenberg correspondence principle, which is a really powerful tool from going from dynamical results to getting out combinatorial results. Okay, this was a version that was used by Furstenberg and Weiss in a paper in the 70s in which they gave a dynamical proof of van der Waerden's theorem, Heinemann's theorem, Schur's theorem, all the theorems that I had listed on at the very beginning. All right, so here's an example of what the dynamical statement is, because all we did was translate now, right? You still have to prove the dynamical statement, which we just haven't done yet. So this is an example of the dynamical van der Waerden theorem, the one that Furstenberg and Weiss proved in 1978. It said, if you give me any system, any length, this K is going to be the length of the arithmetic progression that we're looking at, any point and any epsilon. Nope, that shouldn't say there exists a K. This should say there exists M. Just cross this out, sorry. Let me write that off. That there exists, the erasing doesn't work, of course. There exists an N and an M such that you get this pattern, this T to the MX, T to the N plus MX, and so on, all within epsilon of each other. Okay, so that would be an example of a theorem that proves a dynamical, a combinatorial result starting from the dynamical. Okay, any questions? All right. So what's really going on here? The questions that I'm interested in are not about partition regularity now, but they're going to be about taking a weaker assumption, which is only assuming that you get some density of the integers rather than finitely many pieces. If you chop the integers into finitely many pieces, then clearly the densities have to sum up to the density of the integers, which is 1. So one of the pieces must have positive density. So this is a weaker notion to just assume some type of positive density. And I've given here on the screen 3 progressively weaker notions. So the first, natural density, was the one that was sort of the one that was used by Erdos to phrase things, which said that just on average, you're going to get some percentage, or we're going to all want these all to be positive. On average, you get some percentage of the integers in there. Maybe you get 1/10 of them. Upper density says that the limb sup is going to be positive of the same average. And upper Banach density says that you can move them out. For the purposes of today and understanding what's going on in these results, and when you're even reading, you can just think about natural density to start with. Okay, it'll just simplify things and how you're thinking about it. And so there's a density analog of van der Waerden's theorem, which is the famous theorem of Simoretti, which says that if you take a set with positive upper density, and you can just think of it as natural if you want to make it easy, that it contains arbitrarily long arithmetic progressions. So this is very clearly a density analog of van der Waerden. It immediately implies van der Waerden, but it certainly applies to other sets that are much smaller than what you might get from finite partitions. So again, Simoretti's, there's a dynamical approach to proving Simoretti, and this is what Furstenberg did. And just to show you how you get that, I want to actually take Simoretti's theorem and derive Furstenberg's theorem first before we start talking about the converse, which is more interesting. So this is just Simoretti's theorem rephrased, what I've done here. And so what do I mean by rephrased? So the top version, this is Simoretti's theorem in the traditional phrasing. You take a set of positive upper density, then it contains arbitrarily long arithmetic progressions. But here, what I'm saying is if you fix the density, the length you're looking for, that's the K, is going to be the length of the progression. And you fix a delta, which is going to be the density. Okay, so delta is the density that we care about, and K is the progression length. Then you can find some number n, depending on the delta and the K, such that as long as you color the first n integers for any n bigger than that n, and you take at least delta % of them, so you have at least delta times n of them, that you will already see an arithmetic progression. In other words, it suffices to color finitely many of the integers, the first n of them, capital N, as long as capital N is sufficiently big relative to delta and K, and you get Samretti's theorem out. Okay. This is a nice compactness argument to prove that it's clear that the finite one implies the infinite, and it's a good exercise to prove that the infinite one implies the finite one. So that's just rephrasing it. I've just put it back on the slide so you can keep it in mind. But let's see what this does in a measure system. Not a measure preserving system with a transformation yet. Let's just talk about a measure space for the moment. So here what I'm going to do is fix the same delta. Okay, if you give me a delta and you give me a length K of an arithmetic progression that you're looking for, and you take enough sets, okay, at least capital N of them, where N is going to be bigger than that same delta K that's in Samretti's theorem, and assume that all of those sets are big enough, so they all have measure at least greater than or equal to delta for the fixed delta, then it turns out you must have intersection, non-trivial intersection of those sets. And the important part here is not just that it's any of them, but that I'm taking non-trivial intersection along arithmetic progressions. So in the indices here, right? You see that at the bottom, you see an arithmetic progression showing up there.
So Bryna, you have a question from Chris.
Yeah.
Oh, sorry. Yeah, this was just, we went through this, and this might be a dumb technical question. Do most of the sets we deal with have defined natural densities, or are these sets sometimes like super oscillatory?
Yeah, they could be super oscillatory, and there's no reason to assume actually that the natural density is defined. Yeah. And really the real interest is going to be in sparse ones where, for example, upper Banach density might be positive and the natural density might be 0.
Okay, great. Thank you.
Okay, that's where things get more interesting. But for the purposes of understanding the proofs, think of natural density if you want. Okay, it won't make any difference at this point. Yeah, thanks. Yeah, please interrupt because I can't see the chat if you're putting, I just saw that it was in there now. All right, so what I claim is that Samretti's theorem immediately implies this proposition, okay, which is about intersections in a measure space. And here's the whole proof. So what do? You look at your n, it's big enough that we can apply Samretti's theorem. That's just the first bit. And now you look at the indicator functions of these sets. So 1bn, that's the function, which is 1 sub b of x is equal to 1 if x is in b and 0 otherwise. Okay. Maybe writing in white is not a great color for this. Okay. Then if you take those indicator functions here and you average them, okay, because as ergodic theorists and dynamicists, we can hardly ever say anything without averaging, right? So I take these indicator functions, add them up, and average, okay, that's what I've done here, and then integrate over the whole space. Since every one of those sets has measure at least delta by assumption, the average has measure at least delta. And the whole point of averaging and finding an average being big is it means it has to happen somewhere, right? So there is some point where you get the average is bigger than or equal to delta. Okay, so that point, we'll call it x. And now you have to look at where does x live? So in other words, which of the sets that we started with in the list, B1, B2, B3, which of those does x live in? Okay, which ends? And that is exactly a set to which we can apply Samretti's theorem, this set A. So you apply Samretti's theorem in this finite version, and you get that the A contains an arithmetic progression of length K, which exactly gives us this statement. That's the arithmetic progression. Now, that's a pure statement in a measure space, and we used obviously a really powerful tool, Semrati's theorem, to prove it. Okay, but what if I apply it in a measure preserving system? Okay, so now we're in the context of ergodic theory. Then instead of just starting off with a probability space, so x chi mu, which is how we were doing the proposition, I now have a measurable and measure preserving transformation from x to itself. Okay, so measurable means that if you take a measurable set B in X, then T inverse is in the measure sigma algebra. And measure preserving says that the measure of each of those sets is the same. So what that means, if you do this proposition, if you start off with a single set whose measure is bigger than or equal to delta, all of its iterates, T inverse B, T minus 2B, et cetera, all of those have the same measure. In other words, they're all bigger than or equal to, not less than or equal to. Okay, this is a typo. They're all bigger than or equal to delta. Okay. So what does that do? That tells me that there is, from the proposition, an arithmetic progression. And now the arithmetic progression is showing up in the iterates of the transformation. And you get for free, not just that this intersection is non-empty, but you get that it has positive measure. Okay. So what we have just done is used Semrati's theorem to show that in any measure preserving system, any measurable set, you can find an arithmetic progression such that these iterates here are positive. In other words, we've proven a really deeply theorem using another really deep theorem. We've proven Furstenberg's multiple recurrence theorem. Okay, so to state it really clearly, start off with a measure preserving system. Okay, so T is measurable and measure preserving. And if you take any set with positive measure, that's this B, and any length that you're looking for, you can find iterates such that when you iterate along that, you find an arithmetic progression of length K. In fact, I've written one down as a length K plus 1 there. But same thing as before, the interesting part is actually the converse, that if you knew this theorem, if you could prove using purely dynamical methods, prove Furstenberg, then you would get the combinatorial statement. And so how do you go from dynamics to combinatorics? Well, this is Furstenberg's correspondence principle. And so let me state it clearly here. Is let's say you start with a set A in the integers, and this is a set with some kind of density, positive density. Then there is a system, and it's going to be, we can assume that it's an ergodic system. So it's a minor reduction. There is a system and a set E in that system that is going to pick up the behavior of the set A in the integers. So what that means is, what do I mean by pick up that behavior? It means the set E in the measurable setting has the same measure as the density of the set over in the integers. And that when you start translating the set in the integers, so M1, M2 up to MK are some translates that you look at, and you intersect those translates, that if you look at what you get over in the integers, the density of those translates, a lower bound for those intersections is exactly what's happening in the iterates of the set over in the measure preserving world. So what that means is if you can prove something like these kinds of iterates are positive using something like Furstenberg's multiple recurrence, you get that these things over in the integers are positive. In other words, you have found a pattern that you were looking for. Okay. So this was a deep theorem that was used by Furstenberg to prove Semrati's theorem. And since then, it's been used to prove lots of other theorems, like finding polynomial patterns in sets of positive upper density, meaning that you can start somewhere at some integer in the set and add n to it, and add n squared to it, and add n cubed. That's a simple polynomial pattern, polynomial progression. And this is a deep theorem of Bergelsen and Leibman. There are other patterns, many other patterns. But let me give you a quick idea of how you would prove Furstenberg correspondence. Is you do sort of the same thing that we did in the combinatorial, in the compact case, in the topological case, is you start off with this by infinite, I wrote it this time, sequences with the product topology, and you put the shift on it. okay? T is going to be the left shift here, moving every entry over by 1. And what you do is you define an element, the point A, to be the indicator function of whatever set A over here you started with. So just like we did, this is exactly the same as we did for the topological setting, is you set AN to be 1 if and only if N is in A. Before we had more colors, but here we only have you're in the set or you're not in the set. And now we define the dynamical system that I care about. It's going to take that point A and take its orbit closure. So to answer a previous question, this time we're always going to get something that's going to be transitive by definition, because we're starting with one point and taking its orbit closure. Okay. And now what's the set E that I care about? Well, the set E is going to be all of those elements, the bi-infinite sequences, the sequence in zeros and ones, that have a 1 at the 0th entry. Okay, 1 at the 0th entry is like picking up an indicator function of you're in the set. And you can check, and I'm going to leave you to check some of these details afterwards, but this set E is Clopin. And by definition, it tells me that the iterates T to the NA lands inside E if and only if the N was inside my original set. And you can check that. And this is the point A, which was the particular point that we used, this indicator function right here. Now, that does one bit, but there's a lot more to do here. So this is the continuation of the proof. That's just the statement up there. Is now I have to use the fact that it was density, and I have to check that I can define a measure that will pick up the right statistics. Okay, so by the right statistics is I still need this statement here, that the measures of these things are a lower bound for the densities of the corresponding intersections over in the integers. And so, first of all, because the set A had positive density, there are some sequences that pick up that density, okay, whatever type of density it was. So these are just the big sequences, the big intervals along which you pick up the right density. And you can use that to show that there is an invariant measure, and this is invariant with respect to the shift, that is going to pick up the density of A is going to be equal to the measure of the set E. This requires a little checking. And now I said in the theorem, I wanted to make the reduction that this measure was ergodic. Well, you can use ergodic decomposition. Okay, and if you're not familiar with this, it's okay. This will come back later, I'm sure, when you're reading things. You can decompose the measure that we found here, this one particular measure. We would decompose it and look at it. You get some ergodic measure, which we'll call mu. And so then what happens is the measure of E with respect, the mu measure of E is going to be at least as big as the nu measure, which is equal to the density. And now you have to pass to subsequences still to check that you can get all of these good statistics for any choices of M1 and M2 and check that this works. So there's some work here to do, but this is the outline of how to do those steps. Okay. So the goal, as I started at the beginning, is we want to apply this for infinite patterns. Okay, because right now, all of the patterns we discussed of applying first-order correspondence were arithmetic progressions. I gave you an example of polynomial progressions. And unfortunately, this doesn't tell us anything, because if you were going to apply this for an infinite pattern, over here, if the measures of these intersections start going to 0 as you put more and more terms in, this will go to 0, which will tell you that this is bigger than or equal to 0, which doesn't give you any information. Okay, so unfortunately, as it stands, these intersections could become empty. You don't learn anything from it. And so there was a tool that was introduced, I don't remember the exact year, but sometime maybe in the 80s by Bergelsen, which is a quasi step towards infinite, but not, it doesn't quite get there. It says the following, this is the Bergelsen's intersectivity lemma. Is that if you take a start off with a set of integers, again, with positive density, then you can find a sequence of a sequence BI with positive upper Banach density, such that when you take any finite, and here's where it's why I said it's quasi-infinite, okay, any finite set F, that the intersections over those choices where you translate A minus BI for those guys, where I and F is non-zero, non-empty rather. So I'll give you a quick recap. I don't expect you to follow this in real time, but it was just to indicate what's going on here, is that to understand this intersectivity lemma, what it's saying is you can think about it in measure preserving systems, and that's sort of the way I would prove this, is that you can assume instead of dealing with integers by going through Furstenberg's correspondence, you can think about this as talking about sets, Bn, who are all bigger than or equal to epsilon in their measure. And what this is saying is you can find the sequence Bi that's going to be this subset D with positive upper density, such that you get the same correspondence here, but that's going to be a measure of this intersection is positive. Okay, so I'm doing Furstenberg correspondence to the Bergelson-Lemma statement. And now to prove the Bergelson-Lemma statement, you have the tools of averaging available to you, and you can see what's going on. Is first you have to throw out some places where you might get measure 0. So F is going to be the finite sets, which could be problematic. It's a small set, but it's going to be the bad ones where maybe I got the measures of the intersections were 0. Turns out that's a countable small set. And you do the same thing we did when we proved Furstenberg using Semiretti to prove Furstenberg's theorem, is you average the indicator functions. When you average the indicator functions, as we already saw, the integral is going to be bigger than or equal to epsilon. And so I can look at the lim sup. I don't know if it's a limit or not, right? But I can look at the lim sup of these average functions right here. And I can use Fatou's lemma to do an interchanging of limits. And I just want to point out that right here, going from here to here, there's this inequality here, that's a use of Fatou's lemma. And what it does for us is a very similar thing. So I realize I'm going a little quick and you can stop me with questions, but the reason I want to just say this is to get to a different use of these kinds of ideas that will be more detailed later, and you'll need this later. So when you do this interchanging, you get some point, just like we did when we translated Semiretti into Furstenberg's theorem, where f of x is bigger than or equal to epsilon. And that's what produces the times exactly when this happens is what produces the set that we need. Now, this tool was used by Bergelson to prove some very nice things, which this is sort of this corollary I've written here is really sort of just a restatement of it. But let me tell you the sum set that he got out of this. It's what I really want you to take away from it. Is it says if you start off with a set A with positive density in the integers, there is some set B with positive density, so that the different set A minus A contains the sum set B plus B. And these are infinite, okay, because this set B has positive density, so it must be at least infinite. So the difference here from what we're about to talk about is this is A minus A here, and not the set A itself. A minus A is much bigger than A usually, right? You remember back, it's a nice exercise to show that A minus A must be much larger in size than A. And if you remember back to the measure theory, if you've never done this exercise, take a set of positive measure, for example, in the reals, and look at the differences of all the elements in that set. You must contain a small interval around 0. So that's a nice exercise. So we want to understand more general sum sets and not ones that are in A minus A, but in A. And it turns out that this trick of using Fatou's lemma does not work to do the more general sum sets. And it has to do with this interchanging of the limits. But this problem was solved by Joël Moreira, Florian Richter, and Donald Robertson in a paper that was really a big breakthrough paper, in which they showed that if you take a set with positive density, there exist infinite sets, B1 and B2, such that when you sum any B1 from B1 and B2 from B2, and that's what this notation means, okay, you're taking an element from the first one summed with an element of the second one, that you get back into the set. So their proof, before I go on, their proof used a lot of different tools. It used some non-standard analysis. It used higher order Fourier analysis, functional analysis, harmonic analysis, combinatorial tools, and they used that Bergelson intersectivity lemma in their proof. And in their paper, they conjectured that you can do more terms, that not just can you get double sum sets, B1 plus B2, but you can get finitely many sum sets. Okay, so there are K sets that you can sum them up. But because in their proof, it relied on a Fatou lemma interchange, which only works for two things, the method did not generalize for higher sum sets. Okay. So the theorem one of the papers that you're reading is that you give me a set with positive density, you can find K infinite sets, B1 up to BK, such that all of the sum sets from taking BI from the corresponding set BI are contained in A. And a second paper, which is a shorter paper using the same ideas, is that there is an infinite set B and a translate such that when you take the sum sets of distinct elements, so there's B1 is not equal to B2 here, that you get back into the set up to a translate, a fixed translate. And in fact, one can take the translate T to either be 0 or 1 here. And this has to do with the fact that we're summing two sets here. Okay, so those are the statements of the theorems. And now I will use the time to talk about what type of correspondence principle comes in for these, but maybe this is a good moment to stop and see if anybody has questions.
So I have a quick question in the first result in 2019 there. So we don't know anything about B1 and B2 besides that they are infinite. They have density, positive density, definitely not, right?
So there exists a set A of integers such that whenever you can find two infinite B1 and B2 with this property, neither B1 nor B2 has positive density. So there exists such an example. One can construct it combinatorially using sort of random dynamics to try to do that, random subsets, or it's written explicitly. Such an example is done in a short proof by Host of the same result. Host gave a short proof after their proof of the same double sum set using much more ergodic techniques. And in that paper, he has a short example. So it's nice to look at, written out carefully using dynamical viewpoint to give such a short example. And so what that says, though, is that you cannot just hope to iterate their proof, because there are examples of sets where there is no way to get at least one of these positive density. So you can't just apply inductively and say, okay, now you can keep going.
Yeah, thank you.
More questions?
So in the second result, why do you not want to add the same B1 to B1?
Yeah, good question. The reason I don't want to add it is because let's say you started in your set A was the odds. Okay, whatever you did, if you have B1 plus, if you allow me to sum the same guy twice, it will be even. So you'll never get back into the same set A. So for parity reasons, you have to make sure that B1 is not equal to B2.
So assuming A is odd, it doesn't help to take T also odd?
So yeah, really good question. So you need a more complicated example to get rid of exactly that setting. So when A is, but you can eliminate it for parity reasons to get a problem there. Okay. Yeah, it's a good question, and originally actually it's amusing because I think when Erdos wrote down the question, the original one, he didn't actually write it down for B1 not equal to B2, but it's clear that that's what he meant because of these parity cases.
Okay, thank you.
Yeah. Other questions? Okay, so let's go on. So I'm going to just start with only talk about the two summands. So B1 plus B2. And actually, I would recommend that this would be the way to read the paper, is just for B1 and B2, because it captures all of the difficulties without adding a lot of the notational problems that come up with trying to do case sum sets. And I will point out when I'm talking about this with B1 and B2, what things need to change for K, because there are more technical issues that arise, but this is how I would start reading the paper. So the first thing is, and the first big hurdle is to combinatorially translate this into a different phrasing. So the first translation I'm going to do is, so this is the correspondence principle part, is really the first thing that needed to change. And when I say needed to change, it was in order to do the K-fold sum set or the B plus B plus T problem, we really needed to rethink all of the steps in the proof and not just sort of repeat what was happening. And so when I say we really need to rethink all the steps, that even goes back to the correspondence principle. Okay, so that part had to be rethought. And so first, I'm going to give you a rephrasing of the correspondence principle by starting with rephrasing purely dynamic, a combinatorial question. So what I've written here is A contains a sum set B1 plus B2, and always my B1 and B2, and even if I don't say it, they're always going to be infinite. If and only if you can find two strictly increasing sequences, okay, and so that's what these sequences, C1 and C2 of integers, such that when you look at the set and you evaluate it along the set C1 plus C2, so the nth element of this and the mth element of C2, and you take the limits, that first, what the difference is. So here, this is saying C1 plus C2 is in A. Okay, that's what this is looking at, because the indicator function of A. Here first is the limit as m goes to infinity, and then the limit as n goes to infinity. And here is the limit as n goes to infinity, and then the m goes to infinity. I have flipped the order here, and I'm asking that both of these be 1, meaning that the sum C1 plus C2 is inside the set A. Okay. So this is a rephrasing of the combinatorial of the statement, and it's equivalent to it. And I'm going to give you a proof of this, but I just want to make sure the statement is clear for the moment. Okay, I've rewritten the statement. So in other words, if we could prove this combinatorial, this rephrasing here, you immediately get the sum set theorem that we were looking at. And the advantage I like of this combinatorial phrasing is that this tells us exactly what to look for as to where to interchange the limits and how to do that. I haven't gotten to phrasing it as dynamically yet. So one direction is if you contain a sum set, then you just enumerate the elements of that sum set and you get the sequences C1 and C2. Okay, so there's nothing to do. But the converse, you have to inductively keep applying this criteria here, which is something that we'll want to prove dynamically, to construct the sets B1 and B2. So what do I mean by that? Well, you pick the first element B1, and so it's going to have double indices. So that I pick the element B1, meaning inside the sequence C1, when the index here is always, that means the first sequence, that such that when you take the limit as m goes to infinity, you'll always be staying in the set. And that's possible because I can use this of the limit. Okay, so now B1 is fixed, and I tell you how to pick the first element in the sequence B2. When you look along your sequence C2, you make sure first that it's one of the ones so that it was inside the set. Okay, so B11 plus B21 should be inside A. And now I take the other limit as n goes to infinity. And I insist that when you let this go to infinity, you're still in the set. And that's by using I guess the first one we used, yeah, so that would be using now this one. Okay, that's the other inequality. And now I go back and I pick the second element of the B sequence, the B1 sequence. And so what you have to do is first insist that you get B12 plus B11 inside the set. That's what this statement means. And now you go along the limits to get this staying in the set. C2 along M stays in the set with this fixed B12. So I inductively alternate picking B11, B1n, and then B2n. Each time applying this, either applying this limit being 1 or this limit being 1 in alternating manner. Okay, and that produces the sequences for us. So what this has done is it's translated this question into another combinatorial version. So far, we haven't done anything. But the emphasis is that, the emphasis on this is that now I'm seeing how to do this dynamically, as to where I'm going to have to worry about interchanging limits. So what happens is you already now hopefully are experts on the first steps of the correspondence principle. Is, let's say we start off with my set A of subset of the integers. You associate to it its indicator function. Again, you take the left shift on this and you take the orbit closure of the indicator function. Okay, so we've already done this. And you look at the Clopin set E, which looks at all those ones which agree at the 0th spot to have a 1 there. And when you, this is the first number of correspondence that we went through earlier, is when A has density, you can find some T invariant measure, mu, that gives positive measure to the set E, this set. So far, we've done nothing different than first number of correspondence. But now when we do this for our new combinatorial phrasing, this turns it into a new dynamical phrasing. So I'm really copying what it says there, having gone through the correspondence now. So the first is the A contains a sumset. That's what we're looking for, a sumset of the form B1 plus B2. If and only if you can find sequences C1 and C2, such that when I apply them to this particular point A, which was the indicator function of the set we started with, and I iterate these shifts, okay, so that's T to the C1n plus C2m of A, you land inside the Clopin set where you see a 1, meaning that you were in the set A to begin with. And there were two limits. One is the limit as m goes to infinity and then n goes to infinity. And this one is the opposite. The limit as n goes to infinity and then m going to infinity. And they should both lie inside the set E. So going through correspondence, this gives me a new dynamical phrasing, i.e. a new statement that I need to prove dynamically. Okay. But this is the same statement, the dynamical statement. It turns out what we really prove, and we don't know how to do higher sumsets. So I said I'll point out what's different for lower sumsets or higher. We actually prove a stronger statement than this one that's written here. And when we get to k bigger than 2, higher sumsets, we don't know how to prove this one without proving the stronger one. We can prove it for k equals 2 without doing that, but not higher. And so what do I mean by a stronger statement is here, all we ask that you land inside the set E, but actually we prove that these two limits are equal, which is a stronger statement than just landing inside the same set, whatever it is. In fact, they land inside the set E, but these two limits can be interchanged and they're equal. So it is it's a stronger strengthening of that. So these are the limits that I care about, okay? I put them up there. So just to point out again, this is m going to infinity and then n, and I care about showing that we can interchange them to get n going to infinity and then m. Okay, and I've erased all of the other, where this came from, because ultimately we're going to have to prove a dynamical statement of this form for some particular x. Okay, is that clear? So I need to introduce some notation that will keep track of this. And when I say we're ultimately going to have to prove this for some particular x, this A that's right here is the A that came up as the indicator function of our set. So I'm going to introduce some notation. Let's call this x00, and you'll see why I'm indexing it with 0, 0 in a moment. That'll be the point A. And then when I start iterating this along the sequence C2, okay, so you take the iterates of A along the sequence C2 and let m go to infinity, we'll call that x01, okay. If you go with you start iterating A along the sequence C1, that's the limit as n goes to infinity along the C1s, call that x10. And then the one where you can go either direction, which I haven't shown that these limits exist, but this is just a notational tool for the moment to be able to keep track of these limits. I will want to call that x11, where you go either n first and then m first, or you go m first and then n first. Okay. And what I'm going to have to show in this notation that I've just introduced, the equality of the limits that's written right here, that I'm going to have to show is that when you start iterating things simultaneously, which is the map T cross T on the product X cross X, when you start iterating X00, X01, these 2 points should go to X10, X11, i.e. these 2 points, the first two, X00, this one will map to this one, while this one maps to that one. And at the same time when I do, let me pick a different color. At the same time when I do this, you will also start with X00, the second statement down here. This one will map to that one at the same time that X10 maps to that one. So if you could prove that you can do this iteration, you exactly would get the statement in this kind of switching of the limits that happens. So let me give you another picture of this, because this is an important idea, is that we're looking for points. We have to prove that they exist. These are the points that look like X00, X01, X10, X11, such that when you go in one direction, the C1 direction along this way, you're moving these 2 points over to these 2 points. And at the same time, you're looking for another direction that when you move in the C2 direction, it'll take these 2 points and move them up to these 2 points. And all of these sequences have to be found so that you can do these 2 movements simultaneously in either direction, and you better always end up at the same point up here. Okay, so this is a 4-tuple, X00, X01, X10, X11, that plays a very special role in this limit. And if the 4-tuple satisfies this picture, meaning you take the bottom along C2 and you get to the top, and you take the left along C1 and you get to the right, for some sequences, C1 and C2, we call that an Erdos cube. And showing that there exist Erdos cubes is one of the main tools in proving this theorem. So how many minutes do I have left, Ben?
You have about 5 to 8.
Okay, great. Okay, so any questions about this? What the definition? The Erdos cube is an important thing to understand, and maybe the right way to really just remember it is 4 points satisfying this picture. The bottom moves to the top along some sequence, and the left moves to the right along some sequence, and it better be that you got the same thing over here, because that's the one that you can get to in 2 different ways.
So far, just like translation, we don't have anything.
We haven't proven anything, yeah.
Right.
But I said I was going to focus on translations, yeah, correspondence to get us to the dynamical statement that needs to be proven, and then one has to work to prove the dynamical statement. Yeah. But you're right. We haven't proven anything. All right. So what does need to be proven? Okay, to maybe more answering your question, is that we need to prove the existence of this. This is a 2-dimensional one, the one that I drew there, right? Because it was 2 subset cube, and it such that you can find a cube with the following things. You give me a system, the system comes out by correspondence, some point in A which is generic. So let me define what that means. Excuse me. Okay, a point is said to be, it's written below, a point in a system is generic if when you start looking at what happens to it, average, it should approach the right average. Meaning when you put down delta masses, and along the orbit of that point, so this is T to the NA, and you put down, so the orbit of that point, this is, you can think of this as the left shift in that point that we wanted, but this is a general definition. And you average those point masses, that these measures, you get some measures now on the set, that this converges to the measure that we wanted. So a point is generic with respect to the measure mu, okay? It actually has to do with the measure that we care about, okay? And this convergence happens in the weak star topology. So we're looking for when you take a generic point and you start and you have a Clopin set, it's open set for now, which has positive measure. This will come from the indicator function of the set that we care about over in the integers. that we can find a two-dimensional cube that starts in with x00 being the generic point that we gave you, this A, and it ends inside the set E. So it's not just the existence of an Erdos cube, but it's the existence of an Erdos cube that will reflect the combinatorial properties of the set that we started with. And that's reflected with where you start your cube. The point A is given, a fixed point A, and where you end your cube, that's so that you can guarantee that you have the right kind of patterns, that you've come back to close to where you started. Okay, so that is the statement that needs to be proven in using ergodic theory. And as soon as you have this, by the correspondence principle and the equivalence that we did prove today, this immediately, as soon as you prove this existence of such a cube, you immediately get the B plus B, the B1 plus B2 statement, the two sum set. Now, I just want to draw one picture for you. I hope you can see this color. Is that we had this example, as this was the two-dimensional cube that we were looking at. When you are moving, can you see that purple easily, or should I use a brighter color? It's good. Okay.
You can see it.
Yeah, I can't see it, but I guess you guys can see it. So what we had shown already when we were doing this is the thing we needed to do is that there were these two sequences, C1 and C2, that allowed you to do this motion. And that the 4 points had all these other properties, because I also needed the x00 as a fixed point and x11 had to live somewhere. But when I moved to higher dimensions, the reason I was using this evocative cubic notation of x00, x01, x10, x11 is because the next step, well, let me change colors to a different one that I used for the C's. The next step was to go on and build another a higher dimensional cube, and this is sort of just an abstract picture of what it looks like. It's supposed to be a cube, and then I'm moving over here, and so over here there will now everything will have a third coordinate. Okay, and in the back now there'll be another coordinate. So back here, I guess this is looking like you moved x 101, and hidden back here in the picture is x001 all the way back there, and up here is x101, and over here it's x111. And what you'll have to show is the existence of this is a three-dimensional version, so it's going to be an octuple from x00 up to x111 that will have the same types of properties. In other words, now there will exist not just two sequences, the C1 and C2 that are drawn there, but you will also need a third sequence going this direction, such that when you go C1 or then C2 and then C3, and you end up getting all the way back to the X111, or you do it in any other order, you'll be able to interchange all of those limits. And you start off with this point, you'll end up at x111. You start off at x000, you'll end up at x11, whichever way you went, whether you did the C1 sequence or the C2 sequence or the C3 sequence. And you'll have more properties that this guy is going to have to be your generic point. There's going to have to be this fixed guy that I started with, and this one will have to live in the right spot, land in the right place. So this is how the generalization goes for higher order. Okay, and so maybe that's a good place to stop.
Thank you so much. Does anybody have any questions?
I have a question. So this K subset generalization, sum set, is there any, what more power do we get from it compared to the two version? Is there some combinatorial interpretation I can think of when I'm thinking of the geometry of this problem?
Well, it's the higher dimensional version of the two sum set. So the two sum sets, you can think of it as it's having two infinite sets. And if you were trying to go and prove a version of Heinemann's theorem, which is true for density, you need to get arbitrary sum sets, not just summing two things. So it's on the way towards a version of Hyman's theorem, but it's not yet there for a full density version because there are even stronger things that you could do to make it even worse, that make it even closer to being Hyman's theorem. That's what I
Okay,
mean.
thank you.
So is the like K subset is the conjectures before or
Sorry, say that again.
no? I mean, so the two subset is like conjectures by others, right?
The two subset was conjectured by Erdos. He conjectured the explicitly both the B plus B with a translate and the B1 plus B2 are conjectured by Erdos. The higher order subset, he didn't conjecture explicitly, but he says, and some paper, and one can investigate more general, when he's talking about these things. Also, somebody asked earlier, about the parity obstructions. I was a little concerned I might not have enough time, but if you want to give me 30 seconds, I'll give you a more complete answer to the parity obstructions. Yeah. I wonder if I can. Yeah, I'll use this little space right here. Okay, so the question was, can you, instead of just, if you look at, can you do an IP translated and get it into a set of positive upper density? So if I start with a set A of positive density, and I does there exist an infinite set IP such that, let's call that IP set IP, all right? So the IP minus the fixed translate is in A, right? The question was, what if you use the translate to allow this? Why do I have to worry about the distinct subsets? Well, you can make a really nice parity example due to Ernst Strauss, which he does this. He shows that there exists a set with density as arbitrarily close as you want to A, meaning for all epsilon, there exists A with density D star of A bigger than 1 minus epsilon, bigger or equal to 1 minus epsilon. And A contains no such translate. No translate of an IP. And the way you do it is as follows. This is to capture all the possible parity issues. You take a sequence of primes, P1, P2, P3, growing extremely quickly. So P1 is much smaller than P2, is much smaller than P3. And now you remove from the full integers the arithmetic progressions, all the multiples of those primes, they're like arithmetic progressions. So you remove all the multiples of P1, all the multiples of P2, etc. When you remove all those multiples, you're removing an arbitrarily small amount if you make the primes grow quickly. That's why I want the sequence of primes to be very quick. And then whatever type of summing you want, you'll have at least some number of that same parity class with respect to a prime. And so this will cause parity problems of all types. Okay, so I didn't write the full example, but the example is define your set A to be the full integers removing all the multiples of some very fast growing sequence of primes. Anyway, it's a nice exercise to check that works.
Well, thank you very much. I think that's all the time that we have for questions. So let's thank Bryna again.